Okay, we'll pass to the next presentation by Alexandra Zamboulis, Lignin Modification for Novel High-Density PA Composites. Alexandra is a postdoc researcher in our lab. In the last 5 years, she is chemist with a PhD from Montpellier, France, and the last 5 years, Sait is in our lab, writing organic chemistry with polymer science, and she's responsible and manages our REDONDO project. Alexandra.
Hello, everyone. So today I will present the work we have been doing in collaboration with Creative Nano on HDPE composites with Lignin. So Creative Nano is another partner of the REDONDO project. It's an SME which is based in Athens, and they work on the synthesis, preparation, characterization of nanoparticles, both metal and metal oxides, but also, as we will see today, in the REDONDO project, they have worked with lignin. So as mentioned earlier, lignin is a natural polymer. It's the second most abundant polymer after cellulose, and it is produced in large quantity as a byproduct of the pulping industry. It has complex aromatic structures and can be depolymerized or simplified in 3 basic lignol monomers. It is a highly heterogeneous compound, and its composition and properties depend on the source from which it is isolated, and also the method, the isolation method. This structural variability can be, in some cases, a slight drawback to the larger use of lignin, as in general, it is easier to exploit a stream, a raw product that has a stable, a constant composition and also constant properties. Nevertheless, because it is produced in large quantities, we are looking for valorization strategies. And one of them is the use of lignin as a bio-based additive, which is a bit more straightforward compared to what Dr. Duval showed in the beginning of the workshop. The pros in using lignin as a bio-based additive is that we can, of course, increase the bio-based content of composites, of the final composite, and we can have, in some cases, improved mechanical behavior, and also some new properties that didn't exist in the polymer matrix, such as notably antioxidant properties. On the other side, lignin is a hydrophilic material. That means that we often have compatibility problems with the polymers, which tend to be more hydrophobic materials. To solve some of this problem, we can modify lignin, so we can have a physical modification which leads to a particle size reduction, and also chemical modification on the numerous functional groups we can have in lignin, for example, the hydroxyl groups or the ester here. And one very common reaction is the esterification of the hydroxyl group, which decreases the hydrophilicity, and therefore we can achieve a better compatibility. In the context of the REDONDO project, Creative Nano has performed a physical modification by producing nanocraft lignin, which has particles of about 500 nanometers, and this was achieved by a patented method by using ultrasonication. And the other type of lignin we have used and that Creative Nano has produced are modified lignins. You can see here 3 types of lignin with phosphorus, nitrogen, and phosphorus and nitrogen groups. And these were produced in order to see if we could improve the flame retardancy of lignin. So these modified lignins, along with the chemical modification, we can see here that we have some size reduction. And also, if we look at the thermal stability of lignin, we have a large increase in the temperature where maximum weight loss is observed. So this would mean that perhaps maybe we have, okay, degradation starts at the same temperature or a bit lower than for lignin, but probably we have some higher stability at higher temperatures. Now, the composites were prepared by melt mixing at 190 degrees, and with the lignin content range from 1 to 30%. I'll start with the results on nanocraft lignin and then move to the modified lignins. So the composites were studied by infrared spectroscopy. As you can see here, in the infrared spectra, we can see the absorbances of HDPE. And also, if we zoom in the region which is here, for the composites which have more than 5% lignin, we can see also the characteristic absorbances linked to the presence of lignin. Thermal properties were studied through differential scanning calorimetry. So we can see we have a negligible impact on melting and crystallization temperatures, and we have a decrease in the degree of crystallinity. And when it comes to the thermal stability of the composites, we have an earlier degradation. The maximum thermal the temperature of maximum degradation rate is approximately constant, and we can see we have a larger residual mass at 600 degrees. Moving on to the tensile properties, here we can see that we have achieved very nice results, especially if we up to a 5 to 10% nanocraft lignin content. But of course, as it is often the case in composite material, when we increase too much lignin content, the mechanical properties deteriorate. Very importantly, if we compare the materials with kraft lignin, so the raw material, and the one with nanocraft lignin, which the smaller particle size, we can see that compared to the nanocraft lignin composites have a much higher, much better mechanical behavior with a higher toughness and lower stiffness. So overall, the decrease of size has led to very nice results regarding the mechanical behavior. And finally, the antioxidant potential was evaluated using DPPH method. So as you have seen earlier, lignin has a lot of phenolic hydroxyl groups, and this will bring antioxidant properties to the final composites. As we can see, the antioxidant properties are proportional to the content of lignin. So overall, in this first series of material with nanocraft lignin, we can see that we have a very nice mechanical behavior and also some nice antioxidant properties. Moving on to the composites with the modified lignins, they were prepared with in the same conditions with the same lignin contents. Again, infrared spectroscopy evidenced the HDPE absorbances as well as characteristic absorbances for each type of lignin. The melting and crystallization temperature were not affected importantly by the presence of the filler, and we have a decrease in the crystallinity content. Mechanical behavior is not as good as with nanocraft lignin. It is maintained until 5% content, but then the properties mostly deteriorate. Now, thermal stability. Here we can see that for all composites, again, the degradation starts a bit earlier than without lignin. Nevertheless, in the composites which have nitrogen, which have been modified with nitrogen, we can see that the temperature of the highest degradation rate is shifted to higher temperatures compared to neat HDPE, while when we have inserted phosphorus in the composites, we have a significantly increased residual mass at 600 degrees. Lignin is a hydrophilic compound, so we studied water contact angle to evaluate the hydrophobicity or hydrophilicity of the materials. Neat HDPE is hydrophobic with a contact angle of almost 96 degrees. Based on the type and content of lignin, we have small differentiations. Overall, the materials, the composites which have been obtained with nitrogen modified lignin remain hydrophobic, while the ones with phosphoric, the phosphorylated lignin and the lignin with phosphorus and nitrogen have a mild hydrophilic behavior. Antioxidant properties. The composites with phosphorus and nitrogen have a very low antioxidant behavior, which was attributed to the fact that probably more phenolic hydroxyl groups were affected from the chemical modifications compared to the two other modified lignins. And the phosphorus and the nitrogen ones, the two first ones, have a relatively good properties, especially the composites that were prepared with phosphorus modified lignin. And finally, flame retardancy. As Pilar explained earlier, the flame retardant properties were tested by vertical flame testing. That means that we have a strip of material and we approach a flame at a certain angle, and then the characteristics that are interesting to us are the dripping. So if there are drops of the molten material which fall during the burning, the time it takes for the specimen to take fire, to ignite, and also the time of burning. So that means the time until the whole specimen is completely burned. And these are the preliminary results which were obtained with our composites. So we can see that compared to neat HDPE, most composites have an improved performance because we have less dripping and larger time for ignition and a longer burning time. And overall, probably the modified phosphorus and nitrogen show the highest potential with almost no dripping when 30% of additive is incorporated in the composite materials. So overall, we see that using lignin, we can have composites with new or improved properties compared to the neat polymer matrix. We have the possibility to tailor to some extent the properties of the material depending on the type of additive we will use and its content. Nanolignin has emerged as a very promising bio-based additive. We have obtained promising results regarding flame retardancy that still need to be further investigated. And also one characteristic that needs to be further investigated is the oxidative aging of the composites. Since we saw that lignin can at some extent show antioxidant activities, it would be interesting to see how aging is affected by the presence of lignin or modified lignins. Before finishing, so next week we have another workshop which focuses on safety, sustainability, and material innovation. It is also a hybrid workshop. It is organized by ISQ in Lisbon. And here is an overview of the agenda. So we cover quite a lot of topics regarding functionality assessment, safety assessment, sustainability, and we will also have a session on standardization and legislation. So if you want to find out more, you can flash on the QR code or go to our website. So before finishing, I would like to thank Professor Bikiaris and all the research group. Special thanks to Christina Samiotakis and Dr. Evangelia Tarani, who have been directly involved in the REDONDO project and in the work I have shown here, and also from Creative Nano, Dr. Alexis Grigoropoulos and Dr. Alexandros Felix Tiniakos. Stay tuned to have more news on the REDONDO project, and thank you all for your attention.
Thank you very much, Alexandra, for your presentation, the interesting results.